We got about 6 minutes before class starts.
Hi, how are you doing?
All right, how you doing?
The only question I have right now, what chapters are going to be on this next face-to-face test?
Okay, if you look at the online tests, that's basically the practice test and the online test. They're all more or less the same thing. And I'm looking at it right now to confirm that I'm thinking the right answer. Uh, so on the 28th, which is this Sunday, you have to have practice test three and practice test four done. Practice test three is for the test, and that's chapters 5 through 6, which we'll finish today. And practice test four is supposed to be for the final, but I'm gonna ixnay that because we're far enough behind where I can't get you to chapter 6 by then. So I'm gonna go ahead and unpublish that for a second. So it's just gonna be chapters 1 through 6, basically.
Chapter 1 through 6.
That's for the face to face as well as for the online test. It was going to be 1 through 7, but we've gotten behind, so I can't give you a test on 7 yet.
Okay, so are we just using the a practice test 4
Yeah,
for
for online
7?
three, for test online test 3, that's going to be the practice test now instead of having that 4 that was for face to face test 2. We're now just going to have practice test 3 that covers online test 3 as well as face to face test 2.
Okay.
Sorry,
What is
I've been changing it a little bit today, just because of the problems of not getting done in time and that sort of thing.
That's okay. Okay, I was gonna ask if we could have access to practice test 2 again for chapter 3 and 4.
Oh no, so the way my practice test 3 is made up is it has questions from chapters 1, 2, 3, 4, 5, and 6 all in it. So you're actually getting practice for all of those just by taking that.
Oh, okay, okay.
Yeah, that's part of the thing I do to make sure that everybody's ready for their test. When it gets too late, like when we start getting, up to chapter 11 or whatever, then sometimes I don't put as many questions of chapters 1 through 4 as I do for 5 through 8 or whatever. But other than that, it's pretty much always a self-contained practice test that covers everything.
Okay, thank you.
You're welcome. Good question, though, Christine. I appreciate you asking me. I'm starting about 6 minutes late, but I got Nathan here and I got Christine here. I did tell everyone to go ahead and chat me your first and last name if you haven't done so already. I think Christine might have already done that. Nathan, you can do that. Again, not required to be here, but it is helpful to have that so I know when you came and all that good stuff. So we are starting in chapter 6, and we should finish chapter 6 tonight. This is on Newton's, the chapter that we're in is called Gravitation and Newton's Synthesis. So, what happened was, if you read his Principia, he says something along the lines of while sitting under an apple tree in his mother's orchard, his mother owned an apple farm, and while sitting under it, he was actually at home for basically the plague. They sent everybody home for like a spring break sort of scenario, and because the plague, they realized they didn't necessarily know what was causing it, but they knew that high population areas like where Cambridge was a problem, so they sent students home, and he was sitting out in his apple orchard under a tree, and he looked up and saw an apple, and he also looked up and saw the moon, and at that point he realized that the two were very similar, which it gives you an idea of how brilliant he was. I mean, who looks at the moon and who looks at an apple and thinks they're that similar? But his reasoning being that basically what's going to happen is that apple is going to get filled with so much water and nutrients that it basically that and the stem will be drying out so that it'll get so heavy that the stem will break. And there's a force that pulls that apple down to the ground. And we now know that force is gravity. And in Latin, that was gravitas, which is basically a weighty or a pondersome, something really deep in thought, but it's also weighty or pondersome. So that's why he used it for the gravitational force. But he had already come up with Newton's first law of motion, which was Galileo's law of inertia, and basically he realized that the moon, if it was really going in a circle around the Earth, there must be some force causing the moon moon to make that circle. Even if the moon's holding a constant speed, just changing direction is still an acceleration, and you can't have an acceleration without a force. So we imagine maybe the force that pulls the apple down to the ground is the same as the force that pulls the moon towards the center of the Earth. And he realized that the acceleration of gravity at the moon's surface was 9.8 meters per second per second. And then he also said, well, let's calculate, for instance, the acceleration due to gravity as a result of, he was pondering it being due to gravity, but calculate the acceleration that the moon had. And we did that in chapter 4 in an example. I think it was like 5-7 or something like that. And we got that the actual acceleration was 0.002725 is what I ended up getting in meters per second per second. That was the actual acceleration of the moon when you take into account that the moon's distance from the center of the Earth, from center of the Earth to the center of the moon, is 60 Earth radii, and that it takes 27.3 days to complete one circle around it. You can use that to calculate the velocity, which is 2 pi r over that period. You got to convert that period, of course, to seconds, and then you use v squared over r, and lo and behold, he got the acceleration of the moon was 0.002725. Now, if you consider for a second that maybe force behaves like light, which Newton had been studying a lot, and Newton discovered, for instance, if you have a light bulb and you're a good distance away from it, then the light bulb acts like a point source of light. So it's an itty bitty thing of light. And what he discovered was that if you're a certain distance, let's say 1 meter away from that light bulb, and you measure the brightness with some kind of brightness meter. If you then go from that 1 meter away to 2 meters away, what he discovered was the brightness didn't go down by half, it actually went down by 1/4. Meaning that it's more or less a 1 over r squared principle. So that light degrades at a rate of 1 over r squared. So if you double the distance, you cut the brightness by a factor of 2 squared. If you triple the distance, you cut it by a factor of 3 squared. If you quadruple it, it's 4 squared. Quintuple it, it's 5 squared, so on and so forth. So he reasoned that if the acceleration of gravity at the Earth's surface is 9.8, and if the acceleration of gravity at the moon were to be considered, and we think that the force is a 1 over r squared force, then what we need is how many Earth radii from the center of the Earth the moon is. Well, it turns out the center of the Earth is 60 Earth radii from the center of the moon, whereas the apple was 1 Earth radii from the center of the Earth. So going from 1 Earth radii to 60 Earth radii means that you should divide the acceleration of 9.8 meters per second by 60 squared, because it's 60 times as far. And if you divide 9.8 by 60 squared, you get 0.000, or excuse me, 0.00272. So that was the calculation they did. In that instant, Newton was the only person on planet Earth that knew exactly what force was causing the planets to orbit around the sun, what caused the moon to orbit around the Earth, what caused the Galilean moons to orbit around Jupiter, and so on and so forth. So that's how he came up with his law of gravity. And then he argued that the law of gravity would be a 1 over r squared law. So let me start off by just saying, I'm going to move this real quick and then I'm going to share my screen with you. But hopefully I can move this down a little bit. And then I'll share the screen. Good. Oops. Okay, I definitely want to undo that. Oh well. Let's do paste, and I'll just put it right back where it was. And I'll just leave that and say heck with it. All right, so I'm gonna go ahead and share my screen with you real quick so I can give you a physical description while by writing on my iPad. So iPhone, iPad. The screen should pop up in a second. So that should come on any second now. All right. So first off, I'm going to turn to the last lecture we had, which was on 617, and specifically example 5.9. You see up here at the top in blue. This is the example we worked with the moon, where the period of the moon was 27.3 days. And of course, we converted that to seconds, and that was 2.359 times 10 to the 6. The orbit of the Earth was 3.84 times, or excuse me, the orbit of the moon was 3.84 times 10 to the eighth meters, which is really 60 Earth radii. So if you actually take and calculate the velocity as we did here, 2 pi r over t, you get 1,023 meters per second. I told you that was on the order of 2,000 miles per hour. And then you calculate v squared over r, and we got 0.002725 meters per second per second. So that's the acceleration that the moon has, and that's the calculation that Newton actually did. Now, if you use that, then you can say, okay, well, Newton reaches the conclusion that the force of gravity, F sub g, is proportional to 1 over the distance of separation between whatever two bodies you're calculating the gravitational force for squared. So we'd say force is equal to that. Then he made the reasonable assumption that he also suspected the force of gravity would be directly proportional to the mass of the planet. And by symmetry, he would say it also be directly proportional to the mass of the other thing, so that he ended up saying M1 and M2 as well. To make a proportionality into an equation, you actually just add a constant and put an equal symbol on there, and therefore the force of gravity that Newton conjured up was F is equal to some constant, which we've now labeled or given the symbol capital G, and it's G times M1, M2 over r squared. And he went further by saying this tells us that the force of gravity is proportional to the mass 1. It's also proportional to the mass 2, so that if you double mass 1, you're going to double the force. If you double mass 1 and triple mass 2, you're going to sextuple the force, because 2 times 3 is 6. And if you double the distance away, that's going up, and the fact that the FG is on the numerator on the left hand side and the R is in the denominator on the right hand side, that means it's thumbs up, thumbs down. So if the distance goes up by a factor of 2, then the force is going to go down not by a factor of 2, but by a factor of 2 squared. And as I told you, that also includes if you triple it, it's going to be by a factor of 3 squared. If you quadruple it, it's a factor of 4 squared. Or if you 60-tuple it, then it's going to go down by a factor of 60 squared, which is what we just did when I told you if you take 9.8 and divide it by 3,600, you'll get 0.00272, which is the same, or 273 roughly, which is the same acceleration. So he found that this force was directly proportional to the mass, the product of the masses, and inversely proportional to the distance between them. And he also said that the force acts along the line connecting the center of mass of M1 to the center of mass of M2. Another way you can think of it is you can imagine M1 and M2 are point particles, so they're infinitesimally small, and you just say the distance between M1 and M2 is R, and in fact the force is going to act along that line between M1 and M2. So that was the complete law, and of course there was experiments done, and you could actually do it. The force of gravity is really, really weak, and it turns out that in order for that to be the case, the G, once you do it experimentally, the G turns out to be 6.67 times 10 to the negative 11th, and that's newtons meter squared per kilogram squared. So that number is really, really small. It's literally zero, a decimal point, 10 zeros, and then 667. So it's really, really teeny. That's why you can't necessarily feel the gravitational attraction that you have for, you standing next to a car or you standing next to your husband or whatever. You just can't do that. So it's a really, really weak force. But it's called Newton's universal law of gravitation for a couple of reasons. One, you see that it's a universal force. If two objects have mass, then according to this formula, they're going to have a force of attraction, period. No ifs, ands, or buts about it. So it is universal in that sense. But it's also universal in another sense. Specifically, there is no value of R that you can put in that Newton's law of gravity such that the force is zero. The best you can do is take the limit as r approaches infinity, and then you get the force of gravity zero. So that literally means that the force of gravity reaches across the entire universe. However big that is, it's got to reach across the entire universe. Obviously, very, very small the farther you get away, but still not zero. So that was the big synthesis that he had. So now that we have that, let's go to example 6.1 in your book. And in example 6.1, they're saying the following. Can you attract another person gravitationally? So this is example 6-1. And it says a 50 kilogram person and a 70 kilogram person are sitting on a bench close to each other. Estimate the magnitude of the gravitational force each exerts on the other. So what we have here is M1 is equal to 50 kilograms, and I put a dot there so that we can count it as two sig figs. M2 is equal to 70 kilograms, and I'll put a dot there too so we can count that as two sig figs. And what I'm going to do is if you imagine two people sitting close to each other, it's probably not unreasonable to say they're about a foot and a half apart because what you want to do is imagine where the center of mass of the human is. And most of us are pretty symmetric. So you'd at least say if we're both sitting upright, somewhere parallel to our spine should be where our center of mass is. And if you sit two people next to each other, it's not unreasonable to think that one person's spine is about, 1.5, 18 to 20 inches, say, away from the other spine. So that's what we're going to say our distance is. R is about 0.50 meters. That's what we're going to call the distance apart. So now we can calculate the force. Solution. And this is an estimate problem, so I'll use these two sig figs, but then we'll just round it to one sig fig. The equation we're using is F is equal to G M1 M2 over R squared. So F is going to be 6.67 times 10 to the negative 11th. And I'll put the units on this one, but I probably, because it's so much of a pain to write the units, I'm probably going to suppress them for the future calculations, but I need you to see at least once how it works out. So we have a 50 kilograms right here. I'll put a dot there reminding us it's two sig figs. I got a 70 kilograms with a dot right there. And then I have a 0.50 meters, which again, I added an extra sig fig on that too. So when I do this calculation, I get 6.67 times 10 to the negative 11 times 50 times 70. And then I'm going to divide by uh, zero point 0.5 squared. And I'm going to close parentheses. And that gives me 9.4 times 10 to the negative 7th newtons, which is approximately equal, since 9 is really close to 10, you might as well call this as approximately 10 to the negative 6 newtons. So that's what we mean by order of magnitude or estimate calculation. You don't even need the mantissa portion of scientific notation. You just need the power of 10. That should be sufficient. Notice, or hopefully you noticed that in chapter 1 when you were doing some of the homework. So as you can tell, a newton is about, well, let's say 1 pound is about 4.45 newtons. So a newton is even smaller than a quarter pound. Therefore, you can imagine a millionth of a newton is teeny. So yeah, the force of attraction is really, really small, at least for, objects that aren't the size of planets. There's another example that's really good to do, and this is example 6.2. And this one says spacecraft at 2 times the radius of the Earth. What is the force of gravity on a 2,000 kilogram spacecraft when it orbits 2 Earth radii from the Earth's center? That is, it stays a distance r Earth above the Earth's surface, where r Earth is 6,380 kilometers. The mass of the Earth, excuse me, the mass of the Earth is 5.98 times 10 to the 24th. So what we know is radius of the Earth. Notice I'm using a different symbol for that. We have a symbol from astronomy. It's basically a circle with a plus in it is the sign for the Earth. A circle with a dot in the middle is the sign for the sun. And we actually have them for all the planets, but they're some symbols that come from kind of ancient stuff, but you can recognize them, for instance, because they look a little bit like horoscope symbols. So we have stuff like that, but we're going to use at least this one for the sun and the moon, or the sun and the earth. So the radius is 6,380 kilometers, which would equal 6.380 times 10 to the sixth meters. And we also know that the spacecraft has a mass, little m, that's equal to 2,000. Notice I'm going to put a dot on the end so I can pretend like it's going to have 4 sig figs. And the mass of the Earth, which is the circle with a plus in it, is 5.98 times 10 to the 24th kilograms. So that's the mass of the Earth. The solution here, it requires us to understand that F is equal to G M1 M2 over R squared. And I should say R is going to be equal to 2 times RE. Now, we can plug these numbers in and that works fine, but it's not the smartest way to do it, and it's not making use of something fundamental and something that would make the calculation much simpler. And that is the fact that I just finished teaching you that the law of gravity is a 1 over r squared force. So if we know the force on the spacecraft at 1 Earth radius, we should be able to readily figure out what the radius, or excuse me, what the force is at 2 Earth radii. Specifically, we say F is proportional to 1 over r squared, and that means if r goes up by a factor of n, then F is going to go down by a factor of n squared. It could also do, similar little arrow type things. Ooh, that was supposed to be R. Uh, and actually, let me put the R on the other side. So if R goes up by a factor of n, then F goes down by a factor of n squared. Another one we could say is if R goes down by a factor of m, then F is going to go up by a factor of m squared. That's the scenario that we're talking about as well. So we know that the force of gravity at the surface of the Earth, which would be r1 radius, would be just weight, which equals m times g, and that would be 2,000 kilograms times 9.80 meters per second, like that. And therefore, we have that the force at 1 Earth radius is 2,000 times 9.8, which gives us 1.9 or 19,600 newtons. Now, we only had 3 sig figs there, so I should probably do it like that, but that's 19,600 newtons. Now, what we want to know is the force at R equals, force at 2 times the radius of the Earth. In that case, what we say is, therefore, the radius went up by a factor of 2, and according to our understanding of the law of gravity, that means the force, because the F is on the left-hand side and in the numerator, and the R is on the right-hand side of the equals and in the denominator, that makes it a thumbs up, thumbs down. So that's why I have one arrow up and the other arrow has to be down. But now I've got to implement the part where it's a 1 over r squared. So instead of 2, I'm going to write 2 squared. So that's equal to 4, and that means that the force at 2 times the Earth radius should be equal to 1/4 the force at 1 Earth radius. So if we divide this by 4, it'd just be 1/4 times 19,600 newtons. And if I divide that by 4, I get 4,900 newtons is the force on the spacecraft at 2 Earth radii. See how we saved us a good deal of work just by recognizing that the force of gravity is an r squared law, 1 over r squared law. Again, you can, and I encourage you to do it, try plugging this formula in, or try plugging this data into this formula right here, and you'll probably get like 4,898 or something like that, or you might get 5,000, or maybe you get 4,922 or something, but you're going to get really close to 4.9, or 4.9 times 10 to the third. Any questions on that? All right, let's look at another one. Now, this one's where we're going to pull into some vector quantities. So this is example 6.3. And example 6.3 says force on the moon. Find the net force on the moon due to gravitational attraction of both the Earth and the Sun, assuming they are at right angles to each other, as in figure 6.5. So I'll draw figure 6.5, if you will, like this. So here's our moon. And then way down here is the sun, obviously not to scale. So there's the sun. And what we're imagining is if you draw a line perpendicular to that through the moon, then you'll get the Earth over here, and this is the uh, M sub L, which is what I mean as mass for the moon. Oh, actually, no, I'd use the M just to indicate it was the moon. This one's going to be the Earth like that. So they give us some information. They gave us, for instance, that the mass of the moon is actually equal to 7.35 times 10 to the 22 kilograms. Remember, it was 5.98 times 10 to the 24th kilograms for the Earth. So the Earth is on the order of 100 times more massive than the moon. We also have the mass of the Earth, and that is 5.98 times 10 to the 24th kilograms. And we also have the mass of the sun, which would be the circle with a dot in the middle, and that's 1.99 times 10 to the 30th kilograms. Now, the distance between the moon and the earth, our moon earth, is 3.84 times 10 to the 8th. Make sure I'm remembering that correctly. Uh, Actually, I did it on the previous page. Nope, I did not write it there. Maybe I saw it on the previous page. Thought I wrote it here too. Oh, I remember where I saw it. I saw it right here. Yes, 3.84 times 10 to the 8th. So that was good. I was just in a different place altogether. So that's 3.84 times 10 to the 8th. And I'm realizing how badly I'm writing. So let me make that a little bit easier for you guys to read. And that is meters. And then, of course, we need the distance between the moon and the sun, which is essentially the same as the distance between the moon and the earth, or excuse me, between the sun and the earth, and that's one astronomical unit, which is about 1.5 times 10 to the 11th meters. It's 1.49 if you want three sig figs, 1.49 times 10 to the 11th. I just put two in there, and that should be good enough. Actually, no, let me go ahead and make it three sig figs just because everything else has three sig figs. So 1.49 times 10 to the 11th meters. Now, when we look at this, we got to use our solution, which our solution tells us the equations that we're using. The equation we're going to use is F is equal to G M1 M2 over r squared. We're also using the principle that tells us exactly along what line it acts. You notice I drew a line from the center of the earth to the center of the moon, and I also drew a line from the center of the moon to the center of the sun. So the actual force of attraction will be along those two lines in the two cases. What we have is the total force on the moon, F sub m, will be equal to the force on the moon due to the earth plus the force on the moon due to the sun, like that. So that's the big principle that we got to learn. Now, I'm going to go ahead and draw the force on the moon as a result of the earth, and that force points this way. That's the force on the moon due to the earth. And then the force on the moon due to the sun is going to be F moon, sun, like that. So if you complete the parallelogram, which is what you are supposed to do when you add two vectors tail to tail, then what you get is the total force Fm is that purple force. And your book is actually using this angle right here. When I worked it out, I used the complementary angle to that, but I'll try to do it this time more consistent with the book. So I'm going to say that's the angle. I want to know the magnitude of that force, and I want to know what that angle theta is right there. So how do we go about doing it? Well, the formula gives us the magnitude. So I'm going to go ahead and say the force on the moon due to the earth is equal to 6.67 times 10 to the negative 11th. This is where I'm suppressing the units just because it's a lot of stuff to write. Times the mass of the moon, which is 7.35 times 10 to the 22, and then the mass of the Earth, which is 5.98 times 10 to the 24, and then all of that is going to be divided by the distance between the two, which is 3.84 times 10 to the 8th. And of course, that has to be squared. So now we can do our calculation 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22 times 5.98 times 10 to the 24. And then I'm going to divide this by 3.84 times 10 to the 8th. And I'm going to square that, close parentheses. And this gives me 1.988 times 10 to the 20th newtons, and we really only had three sig figs, so I got to underline that second eight there. Now I'll take the force on the moon due to the sun. This is going to be 6.67 times 10 to the negative 11th times 7.35 times 10 to the 22. This time times 1.99 times 10 to the 30th. I think I wrote that down somewhere. Yeah, I did. That's the mass of the sun. And then now we've got to divide it by that much larger 1.49 times 10 to the 11th squared. So in this case, we get 6.67 times 10 to the negative 11 times 7.35 times 10 to the 22 times 1.99 times 10 to the 30th divided by parenthesis 1.49 times 10 to the 11th squared, close parenthesis. This gives me 4.394 times 10 to the 20th newtons. So you can see they're about the same order of magnitude, but it appears that the force on the moon due to the sun is about twice as strong as the force on the moon due to the Earth. So now we're going to go ahead and since these are at right angles to each other, these two forces, that means the Pythagorean theorem can be applied so that the magnitude of the force on the moon is equal to the square root of 1.988 times 10 to the 20th squared. Again, leaving the units off just because it's a mess. Plus 4.394 times 10 to the 20th. Again, leaving the units off. Squared. If I take these two quantities, 1.99, or excuse me, 1.988 squared plus 4.394 squared, that gives me 23.261. And that is in basically units of Newton squared. But we can say times 10 to the 20th. In other words, I just took the time to not type in the 10 to the 20th under there. Now I'm going to take the square root of that. And this gives me 4.823 times 10 to the 20th newtons is the total force. And again, we only have it to three sig figs. So that's the magnitude of the force on the moon is 4.82 times 10 to the 20th. And now if we want the actual direction, what we're going to do is take the tangent inverse, or the tangent of theta is equal to opposite over hypotenuse, or excuse me, opposite over adjacent, and opposite is the force on the moon due to the Earth, which is the 1.988 times 10 to the 20th, but that's going to cancel out, divided by 4.394 times 10 to the 20th again, but that's going to cancel out, so theta is equal to the tangent inverse of 1.988 over 4.394. So I'll do shift tangent inverse 1.988 divided by 4.394, close parenthesis, and that gives me basically 24.34 degrees. So that's the actual force, direction, and magnitude on the moon. Anybody have any questions on that? Your book came up with 4.77. Uh, that's a slight difference because they didn't use as many sig figs as I did in one case, and they used more in another. So that's pretty normal. No questions on that one? Okay, one thing your book does mention is Newton was able to, he did a lot of things, but for starters, one thing he did was he was able to show that there was, in addition to trying to verify that his laws of gravitation and his laws of physics would reproduce exactly what Kepler had found, which we're going to talk about in a few minutes, he went ahead and went further than that, and he was able to prove the three laws that Kepler had found already using his law of gravity. But he went further. He was able to show that, in fact, you only can have a stable orbit for two types of forces. The force that could cause a stable orbit is force is some constant times the distance, which happens to be what we call Hooke's law. And we use that, for instance, to study springs or to study how a 2 by 4 is compressed when you put larger and larger forces on it, or how a 2 by 4 is stretched if you put larger and larger forces on it. And the other one's the 1 over r squared law. So that's the force of gravity. So he was able to show that you only have closed orbits for those types of forces. And by closed orbit, I mean one that starts at one point and ends up at exactly the same point with the same velocity so that it will repeat itself over and over again. So he was able to show that that was the case only for those types of laws. He was also able to show the shapes of the orbits would actually be conic sections, not just ellipses. And conic sections include circles, ellipses, parabolas, and hyperbolas. And he was even able to show what we now know of as Kepler's third law and Kepler's second law. So one thing he went further and did was what your book is talking about here, which is spherical shells. It turns out that you can work out, and your book has a proof of it in Appendix E. But basically, if you take a spherical shell, so imagine a sphere that you just hollowed out the middle of, and you still have some mass in the outside part of that. What he was able to show was that there's zero force inside of that spherical shell, but also the force outside of that spherical shell acts just like the force of gravity, as if that whole mass was a point particle at the center of that spherical shell. So that tells us we can treat individual masses that are spherically distributed. In other words, if you have the mass evenly distributed over a spherical shape, then you can pretend it's a point particle at its origin. In other words, at its center of the circle, not necessarily origin. But if you pretend like all the mass is constructed in a pinpoint at the very center of the circle, then you'll get exactly the right answer, as long as you don't go inside of the spherical shell and as long as you don't go inside of the spherical mass distribution itself. If you go inside of the spherical mass distribution, what we know is only the matter that's closer to the center that matters. So what do I mean by that? If you, for instance, well, actually, let me draw it with a circle that works a little better. So if you imagine this is a spherical shell like this, then what we're seeing is the force that you would experience right here acts just like the force that you would have if the entire mass was at that dot in the center. But the forces that you might have at a spot in here is going to be zero. Anywhere inside of here, the force is going to be zero. And for instance, what I mean by this is if this distance right here is r, and this mass right here is m, and this mass right here is little m, then the force is going to be G little m big M over R squared. So it literally is acting like a point particle. If, on the other hand, you had a chunk of mass that was spherically distributed, then this whole chunk of mass outside is just going to act like a point particle at the center. So we could again say it's a point particle here. We could figure out what the force of attraction is right there. We might even say that this distance from here to here is r, and therefore, if this was a mass little m and this is a mass big M, then the force here would be G little m big M over R squared. Now, if you want to go somewhere else, let's say we want to take and find out what the force is at this distance, which we'll say is R1, then it turns out that only the mass for R less than R1 matters. So if you want to calculate the force of attraction at this particular location, and this particular location is a distance r1 from the center, then everything outside is not going to matter, and the only thing that does matter is what's inside this radius of r1. Okay, so that's some of the principles that he was able to put together, and that sort of covers what we're calling the subsection within section 6.1, which is spherical shells. I want to quickly show you how we can make this Newton's law of gravity into a actual vector equation. So if we imagine, for instance, a coordinate system, just to make it sort of more concrete, then here would be X, here would be Y, here would be Z. It's important that you always make your coordinate systems right-handed. Again, you do this with your right hand. Your index finger should be the x-axis. Perpendicular to that should be your middle finger, and that's the y-axis. And then perpendicular to both of them should be z, and that's the z-axis. And whenever you do that, if you make a three-dimensional coordinate system, it should match onto this right hand this way. If it doesn't, then you don't want to mess with it because it's a mess. It can still work. It's just a lot of trouble. So always make them that way. Now, what we know is the magnitude is given by F equals G M1 M2 over R squared. But what I'm going to do is, first off, let's imagine one of the masses as a point particle, M1. Let's say it's right here. And I want to show you where that is in three-dimensional space. So this would be value Y1, and this would be value X1. And then we might have another mass over here, and this is M2. And in this case, this is value X2, this is value Y2. And by the way, if we draw a line parallel to that, that will give us Z2. And if we draw a line like this, but parallel to that, then this will give us Z1. So what we're imagining here is there is an actual vector, R1, and then there's another vector, R2, and we need to figure out some mathematical operation between vector R1 and R2 that gives us a vector parallel to the line connecting them. So here's the line connecting them, and I normally would ask my students, what vectors can you think of in involving R1 and R2 that would give you a vector parallel to that black one? Anybody have any ideas on that? Most people jump to cross product, and what you got to remember with a cross product is that gives a vector that's perpendicular to both. We don't necessarily want a vector perpendicular to R1 and R2. Other people say the dot product, which we haven't covered either of those yet, but the dot product is a scalar product, so that can't give us a vector. So it turns out all you're left with is addition and subtraction. And if you add the two vectors, you would have to complete the parallelogram, which would clearly not give the vector there. So it turns out that the vector between those two is either R2 minus R1 or R1 minus R2. Now, if we want the force, let's say F21 is equal to the force on M2 due to M1, that's the terminology we're using. We're using F sub 21 means the force on object 2 exerted by object 1. Okay? So if we look at this diagram, what we would want is the force on 2, which would be drawn over here at this location. We would want that force to be this direction. So that's the actual force of attraction for M2 on M1. It's literally pulling it towards M1. And if you remember how we do subtraction, subtraction A minus B is A plus the opposite of B. So we want a vector that ends right here and starts right here. So we want the R1 to be positive. So this vector from here to here is R1 minus R2. So that's what we're looking for, R1 minus R2, which seems natural for me to call R1 minus R2 equal to R12. So if I do that, then we can say, all right, well, then F21 is equal to G times M1 times M2, and we're going to multiply it by the vector R1 minus R2. But by doing that, we're actually multiplying G M1 M2 by the length of R1 minus R2, which is supposed to be the R squared. So down here in the bottom, we have R1 minus R2, but we want its magnitude squared. Now, if I ignored this part right here, then this part would have the right magnitude. Everybody see that this part has the right magnitude? It's G times M1 times M2 divided by the square of the distance between them. But that's not very helpful. The reason why is because we've got it now multiplied by this quantity, so it's as if this doesn't have a 2 up there, it's just a 1. So what we would do is we'd say, okay, instead of R1 minus R2, maybe we'd put the unit vector in there. And that is a way to do it. And the way you make a unit vector is you just take the vector and divide it by its magnitude. So if we do that, then we get F21 is equal to G M1 M2 over, now I'm going to use the notation R2 minus R1 is equal to R21, and R1 minus R2 is equal to R12, right? So I want R1 minus R2, so that means I'm going to say R12 over R12 squared, and that doesn't work because that would only be correct if this was a unit vector. So I could put a unit vector up there and then that would make it right. But this bothers me because I've got the force F21, but I've got an R vector R12. That doesn't make it easy to remember. So what we do instead is we can say, let's say it's the negative of G M1 M2 over R21 squared R21 hat. So by introducing the negative, we can use R2 minus R1 instead of R1 minus R2 so that they have the same subscripts. Now, generally speaking, it's not good. I mean, it's not something you necessarily want to do is waste time computing the actual unit vector. So what we normally do is we just say, well, I know how to calculate the unit vector. All I got to do is take the magnitude of the vector and divide it by there. So I can replace this with R21 divided by R21 like that. If I do that, then I finally have a formula F21 is equal to negative G M1 M2 over R21 cubed times R21, where R, or actually, where R21 is defined to be R2 minus R1. So that is the vector form of Newton's law of gravity. You could, of course, leave the negative out and then just did it R12, but then the formulas would have differing subscripts, so I didn't really like that too much. But you also notice that it's a little different from what your, actually, in this case, yeah, it's a little different from what your book has because your book uses R12 is the vector from R2 to R1 or something like that, whereas I like to use it in the order of subtraction because really you have to do a subtraction to do it. So it's probably best that you know what the order of subtraction is. That's why I use the subscripts the way I do. Both formulas are exactly correct, except your author is using a different definition of R21 than I use for R21. Any questions on that? Then it's just a matter of remembering that whenever you're dealing with forces, you have to add the individual forces from each of the things. Like when I calculated the force on the moon, I had to take the force on the moon due to the Earth plus the force on the moon due to the sun. In fact, if you were talking about the force on the Earth, then you could say the force of gravity on the Earth is the force of gravity on the Earth due to the sun plus the force of gravity on the Earth due to Mercury plus the force of gravity on Earth due to Venus plus the force of gravity on Earth due to Mars, and then Jupiter and Saturn, Uranus, Neptune, Pluto, the asteroid belt, the comet, or excuse me, the Oort cloud, and the all the different parts of space, basically. So that's how we're gonna do that when you have multiple forces, but that are multiple things causing forces. Now, if you're near the Earth's surface, we've been able to say that our weight, which hopefully y'all realize, the weight is the actual force of gravity. When I say I weigh 250 pounds, what I mean is if you use Newton's law of gravity to calculate the force of attraction between the Earth and me, and then you converted it to pounds, you'd find that that force is actually 250 newtons. So what that means is weight, which equals mg, is also equal to g times the mass of me times the mass of the earth divided by the radius of the earth squared, because no matter what my elevation is on earth, uh, it's not a significant fraction of the size of the Earth. For instance, the distance from the center of the Earth to sea level is roughly what we call the Earth's radius. If you wanted to go to the deepest place on Earth, the lowest place on Earth, that would be the Marianas Trench, the bottom of the Marianas Trench, a specific spot. And lo and behold, you'd find that that's a very small fraction, still different from the radius of the Earth. Or if you wanted to go to the highest point on Earth, which is Mount Everest, you would find that that also is a small fraction of the radius of the Earth. In fact, when we calculate gravitational acceleration, we find that they're less than about on the order of 0.3% different when you calculate gravitational acceleration at the top of Mount Everest compared to the at sea level, or if you calculate the force or excuse me, the gravitational acceleration at the bottom of the Marianas Trench, that only differs from sea level again by about 0.2, 0.3%. But what we've got from this by realizing that weight is both m times g and this big G times m over r squared, we can see that the lowercase m cancels out, and this tells us what gravitational acceleration is. Gravitational acceleration is the gravitational constant of the universe, big G, times the mass of the Earth divided by the radius of the Earth squared. Remember, M Earth is 5.98 times 10 to the 24th kilograms. And remember, the radius of the Earth is 6,380 kilometers, which is equal to 6.380 times 10 to the sixth meters. So that really is, uh, yeah, I'm just making sure I did a conversion right. That'd be 6.38 times 10 to the third kilometers, which would be times 10 to the 6 meters. So if you actually plug this in, you'll see 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24th. Now I'm going to take that and divide it by 6.38 times 10 to the 6. I'm going to square that. And what I get is 9.799 meters per second, which is the same thing as 9.799 newtons per kilogram, which would be sort of the units of the what we call the gravitational field if we really tried to make up such a thing. But the main thing is now you see why it's 9.80. We really only use 3 sig figs, so this last 9 wasn't there. That means this has to round to 9.80. All right, so now we know what that is. Now let's look at example 6.4. It says, gravity on Everest, estimate. Estimate the effective value of G on the top of Mount Everest. And what we're saying is the height of Mount Everest is equal to 8,850 kilometers. And remember, the radius of the Earth is 6,380 kilometers, like that. With that in mind, you can realize that if you take the total distance r from the center of the Earth to the top of Mount Everest, then that's going to be 8, or let's say 6,380 kilometers plus 8,850. Oh, excuse me. That's supposed to be meters. Ooh, excuse me on that one. Yeah, the Mount Everest is not 8,000 kilometers up. It's 8,850 meters. So we'll do that. And that means that this quantity is 8.850 kilometers. And therefore, we can say that the center to the Mount Everest radius is 6,389 kilometers. And what we want to know is G at Mount Everest equals question mark. So we know solution G is equal to gravitational constant of the universe times the mass of the Earth divided by R from C to the top of Mount Everest squared. So I'm going to put in 6.67 times 10 to the negative 11th. I'm going to put in the mass of the Earth, which is 5.98 times 10 to the 24th, leaving off the units just for convenience. And now I'm going to put 6.389. Notice it's a 389 instead of a 380 times 10 to the 6 meters. Oops, don't need that meter there. And I'm going to square that. When I do this, I get 6.67 10 to the negative 11 times 5.98 times 10 to the 24 divided by 6.389 times 10 to the 6th. And then that quantity is going to be squared and close parenthesis. And this gives me 9.772 meters per second per second. So you see it's very close to 9.8. In fact, it rounds to 9.8 to 2 sig figs, but to 3 sig figs is a little shy. And in fact, you can say the percent difference is equal to 9.80 minus 9.77 divided by the average of the two. Notice they differ by zero point 0.3, so this would be 9.8. Let's say 9.7, and then I want to go one more than that, so I want to say that's 9.7, and I need 1.5, so that'd be 8.5 there times 100%, and that's going to be. I'm dividing by the average because there's neither one is really well, one's more important than the other, but in reality, from a physics standpoint, if you're solving for the gravitational acceleration and you want to know Mount Everest, then the 9.772 is much more important. But if you want to know the acceleration of gravity at sea level, then the 9.80 is more important. So there's really no more important than the other. So what we're doing is percent difference instead of percent error, and the percent difference is the difference divided by the average. So I'm going to take 9.8 minus 9.77, and I'm going to divide that by 9.785, and now I'm going to multiply that by 100, and what I get is 0.3066%. So you see that it's less than a percent. In fact, it's on the order of about 3/10 of a percent different from the top of Mount Everest to the sea level. Any questions on that? Now, if you there is an extra credit problem in our module, and it's basically calculating the acceleration due to gravity at the top of Mount Everest, acceleration due to gravity at the bottom of the Marianas Trench, and then comparing them to each other. It turns out, in fact, if you want to think about the Earth being a non-sphere, because it's technically not a sphere, you know that because obviously the surface of the Earth is covered with mountains and stuff like that, and you might think, wow, they're really big. Like Mount Everest is huge, 8,850 meters tall. Well, it turns out that if you compare the height from, let's say, the bottom of a groove in a basketball to the top of an adjacent dimple, that height difference divided by the radius of the basketball, or even divided by the diameter, either one, that difference or that percent is small, and in fact it's actually bigger than the difference between the top of Mount Everest to the bottom of the Marianas Trench compared to the Earth's radius. So a basketball is actually less spherical than the Earth. So that takes into account the fact that the Earth is actually an oblate spheroid where the poles are squished and the equators are a little bit larger. Still, it turns out that that difference is so minuscule that it's actually more spherical than a basketball is, even taking into consideration the dimples and the grooves on the basketball, and even taking into consideration Mount Everest and the Marianas Trench. Anybody have any questions on that?
I have a question.
Yes.
The number for G, that 6.67,
Mhm.
and also the radius of the Earth, are those numbers that we have to have memorized, or will those be provided for us
No,
usually?
they'll be provided if you look at when you go in your on the online homework system, or like in your textbook. If you go to the left-hand side and click on that table of contents, if you go down to the bottom, there's a useful references, and that useful references is basically the documents that I give you when you take an online or a face-to-face test. That's the documents that you'll have, and that includes the radius of the Earth, the mass of the Earth, the radius of the sun, the mass of the sun, all that good stuff. We have to give you all that.
Okay, thank you.
No problem. All right, so let's look at example 6.5 now. This says effect of Earth's rotation on G. So what we're thinking about here, it says, assuming the Earth is a perfect sphere, determine how Earth's rotation affects the value of G at the equator compared to the value at its poles. So I'm going to use this program to make a really good circle that I can't make. Okay. That's going to be represented by the Earth. And what we're going to do is we're going to imagine having a person on top of it standing on a scale. So here's a little scale, and then there's a person standing on top of it like this, and the person has a mass m. And then here's the equator, and I'm going to have a little scale there too, and we'll have that same person standing here with a mass m as well. Okay, so if we draw a free body diagram for the person at the pole, and it's the same for the North Pole as it is the South Pole, only it's down instead of up. So what I'm going to do is imagine a coordinate system that has y pointing up like that, and let's say x just for the heck of it, even though I don't really need the x direction. It's going to be like this. What we're going to have is the mass m right there. We have acting on it a force due to the scale, and that's really the force that you think you weigh at the North Pole. So this is F sub S. You might recognize it's the normal force, right? It's the normal force, but this time it happens to be supplied by a scale. Now, the other force acting on it is the force due to gravity, which is mg. Okay. Now, this for the North Pole, this free body diagram is not accelerating. It's just going around in a circle like that. So the object's not accelerating. It's just spinning around like that. And we're not studying any of the motion going around. So that's completely irrelevant. So we just say an A equals zero. So the summation forces in the y direction equals mass times acceleration in the y direction gives us the following. Fs minus mg is equal to zero. So that tells us the force on the scale at the North Pole is just m times g at N pole. And of course, it's the same thing for at the South Pole as well. Now I'm going to do the same free body diagram. Of course, this one I got to draw it sideways. But now I'm going to say y is pointing this way and x is pointing this way. And I have a mass here that is a mass of m, and we have the scale applying a force right here that's F sub S, and we have the force of gravity applying a force this way that is W equals mg. Now, in this case, the Earth is actually rotating like this. And in order for you not to be thrown off the planet, you have to make sure you accelerate that way. So we can say that the acceleration is actually this way, and it's specifically v squared over r, where r is the radius of the Earth, like that. So now, if we take the summation of the forces in the y direction equals mass times acceleration in the y direction, we get Fs minus mg, notice that's the negative direction, is equal to the acceleration is also in the negative direction, so I need to write negative mv squared over r like that. And from that, we can see that the force on the scale is going to be mg minus mv squared over r. And that's the result we're shooting for. We wanted to know specifically how your weight sort of changes from the pole to the equator. So if you're at the pole, your weight is mg. It turns out if you then go to the equator, and even if you didn't lose any weight, your weight is still going to be smaller at the equator because part of that force that would normally be considered your weight is going to making sure that you accelerate towards the center of the earth, and therefore the difference is mv squared over r. Any questions on that? Now, you could actually, estimate how big that is. For instance, your book is taking the time to do that, and basically they find that the difference in gravity is a difference of about 0.003 G's, which is again comparable. It's roughly 0.3% different from going to Mount Everest. So the effect of going up to Mount Everest reduces your weight by about the same amount as going from the North Pole to the equator. Any questions on that before we move along? All right. So one thing, it's kind of neat. You can actually look it up. Newton actually did write a popular book. He wrote a book that was for basically everyday people, so that he could explain his laws of physics and his law of gravity. And he used some of the same diagrams that he had in his Principia, which was published like in 1687 in Latin. But this one he wrote in English. I think he wrote it in English. It might have been translated from Latin. I don't recall it was. But anyway, when he tried to explain how we could make something orbit like our planets do around the sun or like our moon does around the Earth, what he did was he drew the Earth and then he put sort of a big mountain on top of it, something like this, and then he imagined a cannon firing off the top like this. And what he reasoned was if you fire a cannonball, it might fall and land right here. If you fire it with a little higher velocity, it might land here. Higher still, it might land here. Higher still, it might even land way over here. But in fact, the sort of fastest it can go would be when it lands right here, diametrically opposite on the Earth. If you go just a little bit faster than that, and it might be a little bit more than just a little bit because the atmosphere is trying to slow you down when you fire that thing. So it still has a chance where a slightly faster one might hit here or here or here or something like that. But he was arguing if you can ignore the air resistance, then if you go faster than this one, then what will happen is the object will go around like this and it will just miss the Earth's surface on the other side, and then it'll come back around and hit right here if you ignore the air resistance. So in this case, you can see that this distance is the radius of the Earth plus the height of the mountain, which is significant on this drawing. And this distance from here to here is just approximately equal to the radius of the Earth because I was imagining it just skimming by. I drew it a bit further away just so you could see that it didn't hit, but I'm trying to imagine it just skimming by really closely. Because of that, you see that we have sort of two lengths. We have the length from the center to the top, which is the radius of the Earth plus the height h, and the other one's about the radius of the Earth. So this is actually an elliptical orbit. So at the lowest orbital speed, oops, there's a R in there, orbital speed, the orbit is an ellipse. If you go faster still, it gets closer and closer to a circle. At some higher speed, the orbit becomes circular. And then at some higher speed than that, it or the orbit becomes an ellipse again. And if you go faster still, the next part you get to is like a parabola, parabolic, or hyperbolic orbit. And of course, the parabola you recognize is pretty normal, but the hyperbola you think of as two sheets, but they're slightly different shapes. So what we're saying is one of those would be the orbit. And basically what happens is, if I remember correctly, it goes like elliptical orbit, elliptical orbit, elliptical orbit, circular orbit, then elliptical orbit, elliptical orbit, elliptical orbit. And then if you just give it enough speed that it can reach infinitely far away, then that'll make a parabolic orbit, orbit in the shape of a parabola. But if you give it enough speed that it can make it all the way to infinity and still have some speed left over, then it becomes a hyperbolic orbit. That's what I recall, anyways. But that's basically what we're talking about. And that's what Newton was saying when he said the orbits can only make conic sections. The conic sections are the circle, the ellipse, the parabola, and the hyperbola. And what we mean by that is if you imagine two of those gas station water cups that you see at gas stations, but you imagine them infinitely large, so they go back and forth infinitely far away. If you slice it perpendicular to the symmetry axis, you get a circle. If you slice it at some angle smaller than the sides of the cup, then you get an ellipse. If, on the other hand, you slice it parallel to one of the sides of the cup, notice this side is parallel to this side. So just like I do with that drawing in geometry, when you have two sides that are parallel, you can draw an arrow on them, and then that lets everybody know that they're parallel. So that's what I'm trying to do here. This is a parabola like that. And if you go parallel to that axis, then what you get is a hyperbola, and this is why you have two parts like that. So this is the hyperbola. And that's why they call them conic sections, because they're part of a cone. All right, let's look at example 6.6. This says geostationary satellite. A geostationary satellite is one that stays above the same point on the Earth, which is possible only if it is above a point on the equator. Why? Because the center of the satellite orbit is always the center of the Earth, so it's not possible to have a satellite orbiting above a fixed point on Earth at any latitude other than 0 degrees. Geostationary satellites are commonly used for TV, radio transmission, weather forecasting, and communication relays. Determine A, the height above the Earth's surface such a satellite must orbit, B, such a satellite speed, and C, compare the speed of a satellite compare to the speed of a satellite orbiting at 200 kilometers above the Earth's surface. So A, we want the height, so H geo equals question mark. B, we want V geo equals question mark. And then C, we want V geo versus V 200 kilometers. And just to make sure everybody knows what we're talking about here, I'll draw this circle. And what we're seeing is the radius of this is the radius of the Earth. And then we're saying, in addition to that, we have a height geo, and that's the geostationary orbit there. Okay. So what we have here is from the summation of the forces equals mass times acceleration. We could do this in the radial direction, so I'll subscript it. The summation forces in the radial direction is equal to mass times acceleration in the radial direction. And what we would have in that case, drawing a free body diagram like so, is we could say, for instance, this is going to be the positive y-axis and this is going to be the positive x-axis. And we have a satellite right here that has a mass lowercase m. We have acting on it a force of gravity that is F equals G M m the earth over r squared. And then in addition to that, we have an acceleration equal to v squared over r. So what that gives us is g. Well, let's use a color other than that. I'm going to go back to green. So that gives me g m earth over r squared is equal to m v squared over r, like that. You can see that the m's cancel out, but we also know that v has to be equal to 2 pi r over the period, and the period t is equal to 24 hours. Okay, so that means 3,600 seconds times 24, which is 86,400 is seconds is the period. Now, in addition to the m's canceling out, you can also see that this exponent of 2 will cancel out. And from that, we can see that now we have g, mass of the Earth, radius of the orbit, is equal to v squared. This is where I'm going to go ahead and plug in what v is. So that's going to be 4 pi squared r squared over t squared. So I'm just using that formula for v, but I'm squaring it because the right hand side is v squared. Now, with that in mind, you can see, and there's a couple different ways you can do this, but basically we can say t squared is equal to 4 pi squared over g times the mass of the Earth in this case, and then times r cubed. So this will actually allow us to figure out what r is, and specifically r is going to be equal to the cube root of all that junk, which is going to be g times m. And the reason why I solved it that way is I want you to recognize that that's going to be what we call Kepler's third law. And now you have a derivation of it. So let me just write that next to it. Oops. This is Kepler's third law. There's a little difference in that Kepler's third law is not about the radius of a circle, it's about the semi-major axis of a sphere, of a ellipse, and it turns out to be the same form, but it's a slightly more complicated if you don't assume it's a circular orbit like I did. But anyways, we got gm times t squared. Oops, I should probably stick to the color I was using. Gm times t squared over 4 pi squared, like that. And that allows me to solve for r. And then, of course, we have to subtract the Earth's radius out of it to get the height, but that's okay. We can do that. So here's our cube root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, 86,400 squared, and then all that divided by 4 pi squared. All of that gives me the cube root of, let's figure out what this number is, 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th times 86400 squared. And then I'm going to divide that by parentheses 4 times 3.14159 squared, close parentheses. That gives me 7.542 times 10 to the 22nd. And now I got to take the cube root of that, so I'm going to raise it to the 0.33333 power, because 1/3 is the cube root. So that's 4.225 times 10 to the 7th meters, which is 4.225 times 10 to the 4th kilometers. So we see that this is basically 42,250 kilometers. But the Earth's radius is equal to 6,380 kilometers. And what we know is R is equal to the Earth's radius plus H. So H is equal to R minus the Earth's radius. So if I take, let's say, answer that I just used, the 4 times 10 to the 7th, I'm going to divide that by 1,000 so I can make it into kilometers. And now I'm going to subtract 6,380, and that gives me 35,870 kilometers is what the height is. So that's part A. The elevation above Earth's surface would be 35,870 kilometers. So that's a pretty good distance. Now, if we want to calculate the actual velocity, we can just use that v equals 2 pi r over t, and that would work fine. So for part B, v geo is equal to 2 pi r over t, which is 2 times pi times 42, uh, 250 times 10 to the. Actually, I should probably not be jumping back and forth in between units here. I'm going to say this is 4.225 times 10 to the 7th meters. And I'm going to divide that by 86,400 seconds. And that gives me 2 times 3.14159 times 4.225 times 10 to the 7th. And then I'm going to divide all that by 86,400. And that gives me 3,073 meters per second. And I'm paying almost no attention to sig figs at this point. I'm just writing down everything we have. So uh, just remember that. It's better to keep up with your sig figs when you're doing the homeworks because sometimes it tries to trip you up with that. But I'm not going to grade on that stuff. Anybody have any questions on this part? That 3,073 is about 6,800, almost 7,000 miles per hour. So that's pretty darn fast. Now, if you compare that to the velocity of the orbit at 200 kilometers, then in that case, you don't necessarily know what the period is, uh, but you can still calculate it using that t squared equals 4 pi r cubed, or just using the original equation that we had here. So for part C, we had, let's see, g times the mass of the Earth divided by r squared, or excuse me, divided by r is equal to just plain v squared. So in this case, v is going to be equal to the square root of 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th divided by the radius. Now, in this case, it's 200 kilometers in addition to the 6,380 kilometers. So it's going to be 206,380 kilometers. Or in this case, it would be 200 kilometers plus 6,380 would be like that. And that would be kilometers right there. And that would be a decimal point. So, yeah, that works. And this quantity should really be 2.06 times 10 to the 8th meters. So if I do that, I can say 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. And then I'm going to divide that by 2.06 times 10 to the 8th which is nearly as far out as the moon. And that gives us the square root of 1.936. So V 200 squared is equal to 1.936 times 10 to the 6 meters squared per second squared, which means V 200 is the square root of that. And that gives me 1,391 meters per second. So that's what the velocity at 200 kilometers would be. And I'm trying to find what your book said for that one. I definitely made some kind of mistake there. The work I did was fine, but somewhere I made a mathematical error. So I would just leave this answer off, and y'all can look at it as well on your example in your book, but just let yourself do that as an extra calculation. And you can see the example. It's an example from the book, but anyways, I'll draw a dotted line around it so you can see where we actually went. And I don't know, probably the error happened when I was trying to combine 200 kilometers with the radius of the Earth. I'm sure I made some kind of mistake in there. But what they got was 3,070, which was the same thing we got for our velocity. The height they got was 35,000, which is the same thing, or 36,000, which is the same thing we got. And then ultimately, the velocity that they got was 7,000 miles per hour compared to, or excuse me, 7,000 kilometer or meters per second compared to the 3,000 that we got for this. So at a 200 kilometer radius or height above the Earth's surface, it's going to have to go faster. Okay. Anybody have any questions on that? All right. I should point out to you that the reason that astronauts are weightless when they're orbiting the Earth, for instance, is not because there's no gravity out there. That doesn't make any sense because you know, for instance, that the moon is farther away from the Earth than our astronauts when they're orbiting the Earth in the space station or the shuttle back when we had that or whatever. And in fact, when we went to the moon, that was the only time we got as far away as the moon. So we know for a fact that the moon is being held to the Earth via gravity. So clearly there is gravity there. The real reason the astronauts experience weightlessness is that they're in free fall. They're literally at each instant they're falling towards the center of the Earth, but they're falling at such a rate that the distance from the center of the Earth to them increases by the same amount that they fall in each second. So it's maintaining that circular orbit. It ends up doing that. But that's a key concept to understand. So I wanted to make sure you guys understood that. Uh, let's see. Yeah, they talk about that a little bit. Now, what we're going to go to is Kepler's laws. I'm just going to state the laws and give you some idea how to use them. But here they are. Ooh, I'm really having a hard time drawing a K tonight. So Kepler's laws of planetary motion. Okay, so Kepler's laws of planetary motion. The first one is Kepler's first law, so I'll call that K1. And remember, not only are you supposed to have these laws and principles memorized, you also have to have them memorized as to which one's the first law, which one's the second law, which one's the third law, just like you do with Newton's first law, Newton's second law, and Newton's third law. Now, Kepler's first law is the planets orbit, oops, the sun in elliptical orbits with the sun at one focal point. Now, if you when you covered college algebra slash pre-calculus algebra, you learned about ellipses. You might not have learned about the focal points, but let me explain a little bit to you. So, if you wanted to actually make a circle, you could put a nail in a piece of plywood, tie a rope to that nail, and then tie the other end of the rope to a pencil or a pen, and then with with a little bit of carefulness, you pull the rope really taut and you make sure that you hold the pencil vertical and that the rope is in fact horizontal. And then you keep it taut and you would run like this, and that would make a circle whose radius is the length of the rope from the center of the knot on the nail to the center of the knot on the pencil. That would be a circle. If you wish to make an ellipse, you can do sort of the same thing, but instead of one nail, you're going to put two nails. So if we imagine putting a nail here and putting another nail here, and then we say, okay, I'm going to connect these two nails together with a rope that's longer than the distance between the nails, then I can do this. I can pull the rope taut with my pencil, and then this is what happens. So you can imagine the pencil being that little red circle in there, and that's a particular point of it. But if you keep that rope such that it doesn't go slack and it doesn't stretch or anything like that, then it will actually trace out the shape of an ellipse, which looks roughly like this. So that's the slate shape of an ellipse. This distance from here to here is called the major axis. That's the major axis. And this length, let's say from here to here, we're not that ingenious, so we don't come up with very interesting facts. So this one's going to be minor, the minor axis. If we're going to call one the major, you're probably going to call the other one the minor axis. And then remember, in the time period of Latin and stuff like that, we didn't really have words for fractions, so to speak. So we just used the word semi to represent half. So in fact, the major axis is 2s, where s is called the semi major axis. Now, if you think about it, we said the planets orbit the sun in elliptical orbits with the sun at one focal point. So you might imagine the sun would be, say, here. If that's the case, then I think you see that this distance right here, uh, let's call that A, and this is what we'd call the perihelion distance. It's the distance at which the planet is closest to the sun. Okay. And I'm just going to label it A because I'm going to use it in a symbol in a second. Now, if you imagine the distance from here all the way to here, then this one's called the aphelion distance. Now, if we were talking about an elliptical orbit for the moon, then instead of aphelion and perihelion, we would have apogee and perigee, because geo is the name we use for the Earth in that context. So this distance is going to be B. Now, if you want to figure out some estimate of the average distance between the sun and the planet, then you might take the distance that it's closest and add to it the distance that is farthest, and then take the average. So you add those two and divide by two, and that would be an average distance. So you might say average distance between the sun, and I'll put the average in quotation marks because we're not necessarily doing a calculus calculation of what the average is between all the different distances that are in this orbit. We're actually saying, hey, I think an average would be the average of the smallest and the biggest. So that's what I'm really doing here. So the average distance between the sun and the planet is A plus B over 2. Well, notice that A plus B is 2s. And then if you divide that by 2, you just get s. So in fact, when we say the average distance, that is somewhat equivalent to calling it the semi-major axis. So from that we see that the semi-major axis S is an average distance for an orbit. Okay, so that was Kepler's first law. Now, Kepler's second law, K2, well, let's imagine that ellipse again. Now, you can go hog wild on this ellipse stuff. There's all sorts of cool calculations you can do. You can calculate instead of just, the fact that it's an ellipse, you can calculate the eccentricity of the orbit. The eccentricity is given by the symbol E, and if you multiply E times S, then you get this distance from here to here is actually this distance from the center to here is E times S, and this distance from here to here is E times S. So the distance here is 2E times S, where E is the eccentricity and S is a semi-major axis. The eccentricity, as you get closer and closer to the ellipse being a circle, then the eccentricity goes to 0. But as you get closer and closer to the ellipse getting really, really long, the eccentricity goes to 1. So 1 is for basically it becomes a straight line at that point. But as you get closer and closer to 1, the semi-major axis is markedly larger than the major axis is markedly larger than the minor axis. So that's some other stuff you can do. Now, the other thing here is we can say, like I said, that one of the focal points has the sun in it, and we can talk about the areas that are swept out. So if you imagine the planet orbiting from here to here, then what you could say is it's going to sweep out an area, and that area is called, let's say, A1. This could be day 1 and this could be day 20, meaning it basically took 19 days to get from that first dot to that second dot. Now, if you imagine trying to make the same area on the other side of the orbit, because that orbit is so long over there, it's going to have to be a very narrow slice of pizza. And this orbit is also going to be a distance A1, or that area is going to be an area A1. And then this would be day 1, and this would be day 20. So Kepler's second law is the planets sweep out equal areas in equal time. So that's what we're showing here. If the two periods are 19 days, then the two areas have to be equal, and that teaches us that the planets go slow when they're far away, when far from sun, and they go fast when they're near the sun. Now, this is not what Kepler's second law is about, but I will tell you a good memory device is that this is also consistent with the planets in general, meaning Mercury is close to the sun, so its velocity is really fast. Jupiter is really far from the sun, so its velocity is really slow. So that's completely consistent with that, but that's not what Kepler's second law is really talking about. Kepler's second law is telling you how the planet moves in its orbit at different points. both of these things, the fact that the orbit's a ellipse is a smack in Aristotle's face, because Aristotle made the argument that the heavens are perfect, and if the heavens are perfect, then they have to have the perfect shape, and everybody would agree that the perfect shape is a sphere or maybe a circle. So the fact that the orbits aren't circular is a big smack in Aristotle's face, and that is part of what the Copernican revolution was doing. Is the Copernican revolution was recognizing that and I would say that's part of the scientific revolution. The Copernican revolution is more about us being the third rock from the sun, sort of like us being a speck in a big galaxy, and it says, an arrow pointing this little speck, and it says you are here, or us being, one little leaf on the tree of life. That's the continuous of the Copernican revolution. That we're not special in the sense that we're the center of everything and the whole universe was made for us. That's part of the Copernican revolution. Whereas the scientific revolution is the idea that, hey, we're going to do experiments and observations, and that's what we're going to let dictate our answers. Whereas before that, we just basically said, well, Aristotle figured all this out. Let's just use him. Right. But Copernicus specifically did this to try to get closer to what Aristotle was teaching us. That's why his orbits were circular and fixed speed, and they just didn't work. Kepler comes along and studying under Brahe comes up with this these set of laws, Kepler's first law, Kepler's second law, Kepler's third law, and they turn out to be absolutely correct. And they're correct for all things. Like there's Kepler's laws for the moon orbiting our Earth, and they hold there too, but the values are different. It's still the same principle though. The orbit of the moon is elliptical. The areas swept out in equal times are equal, and so on and so forth. Now, the third law, Kepler's third law, says the square of the period is proportional to the cube of the semi-major axis. That's Kepler's third law. Now, remember, I pointed that out when I did this calculation, right? Okay, I did the calculation somewhere. I can't recall where. Where'd it go? Where'd it go? Nope, not there. Ah, here it is. This is the circular orbit version of Kepler's third law. And that's actually what it is. T squared is equal to 4 pi squared. We can say, and it turns out to be that way even for a non-circular orbit. You get T squared is equal to 4 pi squared over g times the mass, in this case, of the sun times the semi-major axis cubed. But if you use what we know about the Earth, we know that the period of the orbit of the Earth is 1 year, and we know that the semi-major axis of the Earth is 1 astronomical unit. So if that's the case, then this 4 pi squared over gm has to be specifically, since t in years for the Earth is equal to one, and actually I'll call it YR like that, is equal to 1 year, and S for the Earth in astronomical units is equal to 1 AU. This implies 4 pi squared over G times the mass of the sun is equal to 1 astronomical, or excuse me, 1 year squared over astronomical unit cubed. So then you have a nice little equation that says y in period in years is equal to the cube of the semi-major axis in astronomical units. So that's another version of it, as well as this. Okay. So really quickly, let's do an example with this, and then we'll be just about ready to go. So example 6-7, where is Mars? What it tells us is Mars's period, its year, was noted by Kepler to be about 687 days, Earth days, which is about 687 divided by 365 days per year, which equals 1.88 years. That is the period of Mars. And it says determine the mean distance of Mars from the sun. So what they want to know is the semi-major axis of Mars is equal to question mark. It says Mars was noted by Kepler to be Mars's period, its year, was noted by Kepler to be 687 days, which is 1.88 Earth years. Determine the mean distance of Mars from the Sun using the Earth as a reference. So, what we know is that T squared is equal to 4 pi squared over G times the mass of the Sun times S cubed. And that's true for all the planets. So, T Earth squared is equal to 4 pi squared over g mass of the sun times s earth cubed. And we also know that t Mars squared is equal to 4 pi squared over g mass of the sun times s Mars cubed. I'll call this equation 1, I'll call this equation 2, and now I'm going to say 2 divided by 1 gives me the following: T Mars squared over T Earth squared is equal to 4 pi squared over G mass of the sun divided by 4 pi squared over G mass of the sun, and then times S Mars cubed over S Earth cubed, like that. The reason being is now we don't have to calculate the 4 pi squared over g m. And from this, we can say that S Mars, actually, let me go back to blue again. S Mars cubed is going to be equal to T Mars squared over T Earth squared times S Earth cubed. Well, we know Mars is 1.88 years. We know Earth is 1.00 years. And we know the semi-major axis of Earth is 1, well, let's go ahead and call it 1.00 AU. And that quantity is going to be cubed. So we get that this is 1.88 squared is like 3.534. Notice the years cancel out, so we can say this year cancels out with this year, and I'm left with just AU cubed. So now S Mars is equal to the cube root of S Mars cubed, which equals the cube root of 3.534 astronomical units cubed, like that. And when I take that, I'm going to raise it to the 0.33333 power, and this gives me 1.523 astronomical units. And that is the semi-major axis of Mars, is about 1.52 astronomical units. Any questions on that? Now, notice you could have just used the version that I gave you. Specifically, the version I gave you was t in years squared is equal to 1 year squared over astronomical unit cubed times s in astronomical units cubed. So you could just use this equation outright and it does the same thing, but they didn't introduce that equation, so you had to use this little trick right here to get rid of the 4 pi squared over gm. You could actually just calculate the 4 pi squared over gm, but it's just not very fun doing that. So there's two ways you can do it. Hopefully one of those are helpful to you. Anybody have any questions on that? Your book does example 6, 7. This is the way we actually do work out when we find a moon or a planet orbiting the sun. If we want to know the mass of the planet that the moon is orbiting, or if we want to know the mass of the sun that the planet's orbiting, we can use Kepler's third law doing this. So all we need is the square of the period of the thing orbiting something, and then we can use the semi-major axis cubed, and from that solve for the m what I call the M sun, but it's going to be true for all planets. Whatever's doing the orbiting, the number in between the t squared and the s cubed is going to be 4 pi squared over g times the mass of the planet, assuming that the thing that's being orbited is really, really massive compared to the thing that's doing the orbiting. When the two things get comparable in mass, then there's another formula that you'd have to derive, and that takes into account both of the masses. But it turns out when the mass is really insignificant compared to the mass of the thing that's it's orbiting, then this is plenty good. The 4 pi squared over gm is plenty. But that's what example 6.8 is about. Now, your book goes on from there and talks about Newton's synthesis, the tides. For instance, you can tell because F is equal to GM over R squared. That means that a larger distance away means a smaller force. So if you think about the sun and the earth and the moon, we saw that the force of attraction between the moon and the earth are about a factor of 2 within each other. Well, if I have the earth, the sun, and the moon here, so this is the earth, this is the sun, and this is the moon, then the sun is pulling really hard on this side of the earth closest to it, so the ocean stands up really high there. And on the opposite side, the sun is pulling very weakly so that the mass of earth of the oceans bulge out there as well, because remember, this is sort of like centrifugal, even though it's not a real force. It's like a centrifugal force, so the water's trying to go straight ahead instead of follow the orbit that the earth is doing. So the water stands out on the far side of the earth as a result of the sun as well. Now the moon does the same, or the moon does the same thing. So the moon pulls the ocean out a little farther on this side because it's stronger, because it's closer. But it also releases the ocean on the far side because it's weaker. So what happens during a full moon is we get a what we call a spring tide, and it's called a spring tide because the water appears to spring up really high. In other words, you have really high tides and really low tides. So these are spring tides, and that occurs at full moon, but it also occurs at new moon. Okay? If, however, you had, let's take it over here, if, however, you had the sun here and the earth here, and then you had the moon up here or the moon down here, in this case, the moon is trying to pull the ocean up high on this side and releasing it up high on that side, but then the moon is doing the same thing, pulling it up high on this side and releasing it on that side. So we get what's called neap tides. And that just means they're not a really high tide and they're not a really low tide because the moon and the sun are both fighting to make the water higher along the line connecting the center of the earth to the center of the moon and along the line connecting the center of the earth to the center of the sun. The sun has a slightly larger strength, as we saw earlier, so the tides will be aligned with the moon, excuse me, with the line on the earth to the sun more so than the earth to the moon. But that's what that entails. So all of this we can learn just from understanding Newton's law of gravity. But that being said, it didn't work out so well. There was a problem even when Newton came up with it. Newton knew, hey, this is weird. It's as if the sun is reaching out across space and pulling on the earth without touching it. That doesn't seem reasonable. That's called action at a distance. But he knew that he was getting all these results that he could explain about nature and reality if he just ignored that fact. So he thought it best to just ignore that. And then later on, some other scientist might come along and fix it. Well, other sciences tried to do what we did with electricity and magnetism. They made what we called a gravitational field, but that didn't work out so well. It took Einstein in 1915, or actually roughly 1911, somewhere 11 and 15. It took Einstein all that time to figure out basically what it was. What Einstein discovered was that there is no force of gravity, but rather there is a four-dimensional space-time. So we've got in out, that's like our x direction. We've got left right perpendicular to that. That could be like our y direction. And then we got up down perpendicular to both. That could be our z direction. But then we also have the time direction, which is a fourth dimensional that is perpendicular to those first three. We can't see that because it's four dimensional and we're not very good at seeing in four dimensions. But what Einstein was able to show is that space time is a four-dimensional space, and that mass in space makes space warp. Sort of like when you lay a bowling ball on a trampoline, the trampoline wells down below the bowling ball. Now, if you take a BB and you roll it on that trampoline, not towards the center of the bowling ball, but let's say towards the outer edge of the bowling ball, then what will happen is the BB or the marble or whatever will come get into that depression in the trampoline and then go around it like this. It literally starts like an orbit around it, but friction will catch up to it and the ball will just spiral into the bowling ball. The marble or the BB or whatever will spiral into the bowling ball. But that's really what's going on with gravity. In fact, Wheeler said, matter tells space how to curve, and then space tells matter how to move. So what's going on is there's not necessarily a force of attraction between the moon and the earth or between the earth and the sun. Instead, the earth and the sun and the moon are all just trying to go straight, but space is warped in such a way that their straight lines make orbits around stuff. That is one of the major conclusions of general relativity. There's also something called the equivalence principle, which basically says, hey, you can't tell the difference between gravitational pull, a gravitational force, and just the reluctance to accelerate that comes when an object is accelerating. So, what do I mean by that? Well, imagine this. Let's take a spaceship, and let's say the spaceship has a rocket booster that's going to fire fuel out the back end. You should make noises like this when you're doing it. Okay? And it's basically thrusting stuff out so fast that the spaceship is accelerating at 9.80 meters per second every second. If you're inside of the spaceship standing on a scale, then you figure out that your weight is just m times g. And if the spacecraft is perfectly silent, you can't tell whether you're actually taking off in a spaceship accelerating at 9.8 meters per second, or if you're just sitting still on a launch pad on the surface of the Earth. Oops. On the surface of the Earth, which oddly is spelled with a G now. So here's our scale here, and lo and behold, we weigh the same thing, W equals mg. So this is the equivalence principle. The equivalence principle says you cannot tell the difference, at least on a small scale, between a force of gravity acting downward and a result of inertia making you try to sit still when you're taking off at 9.8 meters per second. Now, if you want to understand why this is only true in a small scale, imagine this. Imagine that this is the Earth, and instead of your spacecraft being that itty bitty thing, imagine this is your spacecraft. If, for instance, it really is a spacecraft with these rocket boosters like this, and it's going up at at a equals 9.80 meters per second, let's say without the Earth for starters.
Okay, so I'll erase that Earth right there. Then if you stand right here and drop a ball, the ball will go straight down. If you stand right here and drop a ball, the ball will go straight down. If you stand right here and drop a ball, the ball will go straight down. If, on the other hand, you are on the surface of the Earth like this, and it's actually gravity, what we call gravity, that's actually doing the pulling, then if you're standing right here, oops, I'm using my eraser instead of my pencil, and we drop a ball, then this ball is going to fall towards the center of the Earth. If I stand right here and drop a ball, then this ball is going to go straight down. But if I stand over here and drop a ball, then this ball is going to go that way. So you can see that on a large scale, the accelerations due to gravity would be in different directions, and you could sense that, oh, this is the gravity force, whereas that spacecraft was an acceleration in the upward direction. So that's sort of what we're talking about with the equivalence principle. And for instance, if you wanted to understand like the what we call the aberration of starlight, which when Einstein came up with his equations, the first thing he did was we knew that the perihelion of Mercury precessed, meaning it was sort of a spirograph thing. So if you imagine this was the sun, and well, actually, if you imagine this was the sun and this was the orbit of Mercury, which is not nearly this elliptical, then what you really see is instead of that being the orbit of Mercury, the orbit of Mercury actually does something like this. And we knew exactly how much that axis moved. Einstein applied his general theory of relativity to it and got exactly the right result. So that was the first thing. The other thing he did was he said, if we look at a distant star near the sun during an eclipse, then we should see that the distant star will have moved. And that's called the aberration of starlight. So if you imagine, for instance, looking at a star, say our star is way back here and the sun is right here, well, according to general relativity, the star being here, our sun being here, would actually cause a gravity that would take the sunlight, which is going out in every direction, and it would bend it. So what would happen is this beam of light would come over here. This beam of light could actually come over here as well. But let's say we focus on this one, and we're used to seeing starlight traveling in a straight line. So what we would say is the star appears to be here, but it's actually here. And the reason why we think it's over here is because this light bent and came to our eye this way. This angle right here, Einstein calculated and predicted, and then Arthur Eddington went out, observed overnight an eclipse, and then got the result. And the next day, he was able to show definitively that Einstein was exactly correct. And in fact, Einstein goes on tour around the United States after this because he becomes instantly famous. I mean, literally, I think it's like the New York Times wrote, God said, let there be light. And then Einstein told it how to move. It was that big a deal. Everybody realized this was really a big deal that Einstein had predicted something that no one had ever seen. And anybody could have seen it at any point in time just by hearing about it. So he goes around touring all over the country and he gets to Great Britain. Sir Arthur Eddington is the astronomer royal for Great Britain, and he's the one that confirmed this experimental result. And of course, the British press were like, "Well, we want our guy to get some fame or whatever." So he said, "Professor Einstein, what can you tell us about Professor Eddington?" He said, "Well, he's a good enough fellow, but he's not a very good scientist." And they said, "Excuse me, he proved your theory was right. How could you say that?" He said, "Well, because
when Eddington was trying to check to see if my theory was right, he stayed up all night worrying about the results. But I slept like a baby because I knew if my results were wrong, God was wrong. So Einstein slept like a baby because he knew basically his laws were consistent with God. It's kind of a crazy thing. I should say that it's not as sacrilegious as it sounds because Einstein believed in a God of Spinoza, which is sort of a logical God that has to exist. There's no way you can say this God doesn't exist. So it's not really he's not seeing God as Jesus. Let's put it that way. So, anyways, that's general relativity. That's a little bit of the intro to it. I can give you more information. This is what I did my research on when I was in graduate school, or at least when I was in the PhD program. But I was orphaned, so I never finished. But I did, get to study general relativity and black holes and cool stuff like that. So, you guys are free to go. I'll wait here till the last person leaves. I know Christine still has a question. Hopefully, I can work that out now. But you're free to go. Remember, you have an online test and a face-to-face test that's coming up on the 28th. Both of those are due that same day. Make sure you get those done. Don't forget. And I will see you again Wednesday, guys. Or excuse me. Yeah, Wednesday. Sam, did you have a question before I get started with Christine? Because I saw you came in a little late. Just want to make sure you weren't here for a specific question or something.
Um, can you hear me?
Yes.
Uh, I was just gonna ask if we could do the same situation with the second test where I take it with Proctor. If you're okay with that.
Yeah, are you going to use a testing center or what proctor?
Um, I'm just gonna go to the testing center.
Okay.
Um,
So
the
would you want to do
Chesapeake
that
Testing Center.
like Friday, Saturday, or Monday?
I like doing Saturdays since that's
If you
it's
can
my day
get,
off.
yeah, just make sure you can get a time schedule with them because it's a different campus that does a Saturday like every week or whatever. So make sure you get a appointment with them. When you get an appointment with them, they'll send me a email letting me know that you're coming on that day, and I'll make sure I have it set up for you.
I'm I don't think they've changed anything, but yeah, their Saturdays are 9 a.m. to 12 p.m. So
Oh, really? It's just open, and you're talking at the Virginia Beach campus or Chesapeake or what?
I'm going to Chesapeake campus.
Okay, that's cool. Long as you can get one in and you can confirm your appointment, then that's fine with me. I'm okay with it.
All right.
All right, thanks, Sam.
Yeah, I'll set that up. All right. Thank you.
Thank you. Have a good one.
All right. Bye. You too.
All right, Christine, I'm pulling up my email now. All right, so it says the three forces represented in figure 410 act on an object. What is the direction of the acceleration of the object? Ah, so in this case, you're going to have a x component that is 4 to the right and then 2 to the left, so that would be 2 to the right, and then 3 to the left, that would be negative 1 to the so that'd be 1 to the left. And then the y component would be 4 up plus 3 up would be 7, and then minus 2 would be 5. So it'd be 1, 5. It would be over to the left 1 and up 5. And they're saying you said counterclockwise from the z-axis, I mean from the positive x-axis. I'm looking at counterclockwise from the x-axis would be greater than 90 degrees. So I'm looking at tangent inverse of 1 divided by 5. And that gives me 11.31 degrees plus 90. So I'm getting 11.3 degrees counterclockwise from the positive y-axis. Let me help you. It might be that you had problems with adding. Notice the rightmost vector. That is a vector that has an x component of 4 and a y component of 4. So I'll call that vector A, and that's 4 I hat plus 4 j hat. And then
So
the
yeah, I think my question
Hmm.
Because wouldn't the 78.7 counterclockwise from the x-axis be the same as 11.3 counterclockwise
Oh,
from
okay. I
the...
see what you're saying. Yes, but that's from the negative x-axis, not from the positive x-axis. If you went 78.7 up from the left side, that's the negative x-axis. So it would be clockwise from that one. But if you went counterclockwise from the positive x-axis, that would still have you in the first quadrant. This one should be in the second quadrant.
Oh, okay. Okay.
Did you get your vectors right when you added them? So I've got the vector in the second quadrant is negative 2, 3. So that's b is equal to negative 2 I hat plus 3 j hat. And then the one in the bottom left, I'm going to call that vector c, and that appears to be negative 3, negative 2. So when I add those, I get 4 plus 3 is 7 minus 2 is 5 j hat. And 4 minus 2 is 2 minus 3 is negative 1 I hat. So yeah, it's to the left 1 and up 5. And it sounds like you got the right angle because 78.7 is the complementary angle to the 11.3 I got, but I think you just didn't understand what it was in that side. What I got was, if you look right here, it goes over 1 and then it goes up 5. So this is the vector that we're talking about.
Okay,
And
I must
this,
have been looking at it wrong then.
yeah,
I
this is 11.3. That would be 78.7,
yeah.
but not this because that would be right here. Did you get a vector that was in the first quadrant, or did you get a vector that was in the second quadrant? Or
I
do you
think the
remember even
first
quadrants? So I
quadrant.
get that.
I think the first quadrant. I guess I didn't like do the calculations right then, because
Gotcha.
I think we got the first quadrant. But okay, I definitely need to work on that problem then.
Yeah, I will tell you what I had was A was 4 I hat plus 4 j hat. B was negative 2 I hat plus 3 j hat. And C was negative 3 I hat minus 2 j hat. So when you add the two, I got negative I hat plus 5 j hat is equal to the resultant. And that's why I have the 1 pointing to the left and the 5 pointing up. Does that make sense?
Oh, yes. Yes, it does. Okay.
Okay.
I understand it a lot better now. Thank you so
Yeah, the fact that
much.
you got the 78.7 tells me you did something right. You just probably dropped a sign somewhere or maybe a little arithmetic error, or you might have just got discombobulated doing it in your head. And that's a very easy thing to do. It's very easy to make a careless mistake like forgetting whether a component's positive or negative.
Right. Sometimes the little algebra stuff gets me.
Yep, yep. But it sounds
Okay.
like I said, you were doing it right, so that's a good thing.
All right. Thank you so much.
No problem. Have a good one. Take
You
care.
too. Bye.
Bye bye. All right, so I guess that's it. Have a good one, everybody. Bye bye.